complicated, because if it's a complicated mechanism, then implementation of this may also have bugs and it could create problem. So it should be simple implementation so that it can be verified, it is verifiable. And every access to any resource should be checked for authorization. But in reality, this could create problems because it could slow down the system. So most of the system may check the authorization only at when the privilege levels need to be escalated. But then this could lead to security challenges. The design should be open so that other people can also verify that there is no problem with the design. And as long as possibly the sharing should be as minimum as possible, because this is the sharing where the data could be passed on or leaked on accidentally or intentionally or unintentionally to the other process or to the other systems. And it should be acceptable. As we said, we talked about access control matrix. So in access control matrix, the rows are representing user. When we talk about user, it could be actually a real user, it could be a process also. And columns are representing objects. And we said that some of the books, they use the term subjects and objects. So subject will include user and process, and object will include all the resources as well as the subject also. So each cell records the access rights of the respective subject on the corresponding object, whether the user is an owner, or it can have a read access or write access or execute access, or in case of directory, a search access, and so on. But the problem with the access control matrix is that it is very large, because the number of, and it will dynamically change because the number of users are changing, the number of the processes which are being run are also changing. So it is a large matrix and it is sparse. Most of the entries may not are empty. So generally, it will be either implemented as an access control list or capability list. So basically, access control list is looking at the columns basically. So for every object, we are keeping information on the object and who has got the access right to the object. So access control list is basically somehow we are keeping only the information about the columns. And only the non-null part. So we are going to keep information about this, information about this. So basically, we are preparing a list of users who have access on a certain object and what are the access rights. Whereas a capability list is for every subject we are checking, we are keeping information on what is the capability of this subject. So whether this subject can access the file or whether the subject can delete a file, etc., etc. So generally, most of the systems will keep both the information in some form. So if we look at the access control matrix, so access control list will look something like this. So file 1, these users can access. File 2, these users can access with these rights. File 3, these users can access with these rights. And this directory, these users can access with these rights. And capability list will look something like this, that user 1 has got this something. Okay. So basically, access control mechanism will be designed by some kind of access hierarchy. So depending upon the hierarchical structure, the privilege right will keep on increasing, and the topmost entity at the hierarchy level will have the highest privileges. And as we go down the hierarchy, we'll find that the privilege levels are getting reduced. They are subset of what is the one having the at the top end. So there will be some authorization list, which is like for a particular object, who are the subjects which have got access to that object and what kind of access is permitted to those subjects. Generally, capabilities are actually represented as a kind of they are implemented. The way the capabilities are implemented is something like a token or a ticket for an object, and the user or the process will present his token or ticket, and then it will be matched with what whether those operations are permitted for that particular subject on that object or not. So possession of a capability authorizes the access to the object. Now at higher hardware level, the hardware is the set of the instructions that the hardware provides are divided into different parts, and they are actually represented as rings in case of Intel architecture. Ring 0 has the highest privilege, so it is something like that we have ring 0, ring 1, ring 2, ring 3. So naturally at ring 0, all the hardware instruction can be executed, and this is the highest privilege. So all the instruction can be executed. Ring 1 will have access to to all the instructions except for some instructions which are allowed only in ring 0. Ring 2 will have again subset of so here let's say I is the instruction set. So at I0 you can access a complete instruction set. All the instructions can be executed at ring 0. But at ring 1 it will be a subset of I0. It is not going to be a proper subset because they will never be equal. So there are some instructions which are not allowed at ring level 1. Similarly, at ring level 2, some instructions will not be allowed and it will be a subset of I1. And then there is I3, which is subset of I2. So it means there are some instructions which cannot be executed at the third ring level. So this is the level which is having the least privilege, and this is the level which is used for user mode. Generally, most of the operating system are actually built on using ring 0 and ring 1, ring 0 and ring 3. So ring 0 is generally used for kernel mode, and ring 3 is used for user mode. Okay. So at ring 0, so now there are other intermediate modes also which could be actually used for, let's say, for example, we want different administrator, but they should not be having as high access as kernel. So kernel may be allowed to access some of the operating system parameters, but let's say we will allow at ring 1 some access to the hardware, but we may not allow the change in the configuration parameters or change in the settings of the various hardware and operating system structure. So we can go for ring 1. So operating system still remains in the control, but this process has much better, has more privileges than a user process. So maybe database administration or database administration process could be launched here. So some supervisor processes may be launched in ring 1 and ring 2. But as I said, that most of the operating system, including Linux, they allow only ring 0 and ring 3. So as I said that we talked about two things, access control list and capability list. So access control list is basically just keeping the non-empty entries of the column of a access control matrix. So for every object, we are keeping information about what subjects can access this object. Now the problem is that uh, 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 as I said, that one of the basic problems that we encounter in security, and which can lead to some loopholes and attacks, is that every access is not verified by operating system or going forward. If we are talking about access in internet access or access to a web server, every access is not verified by the server or by the operating system, and this can create problems. And why every access is not verified? Because every access, if the operating system verifies each and every access, then the then it can lead to a slowdown in the system. For example, the credential of a user is verified only at the time of the login. Then once a user is, and then whenever the user tries to access a resource, the operating system is not going to ask for the user credential again. It will assume that this is the same user. And depending upon what rights of those users have been kept recorded in the operating system tables, accordingly the user will be allowed that access. So for example, let's say a process opens a file. At that time, the OS will check the authorization list, whether this process can open the file or not. But once the file is opened and that file descriptor is available with the process, then any access through that file descriptor is not again verified that whether this file descriptor is with the process or not. So once so for every read and write, the same authorization is not checked. So if a write has been revoked after a file is opened, the revocation takes place only after the file is closed. So between this time, even if the right of the use process has been taken back, there is still some time in which the access is actually unauthorized, but the user or process is able to access the file. So naturally, if you look at the memory access, the way the memory access is implemented in the system, every memory access is checked at hardware level whether this is a valid memory access or not. But the same is not true for accessing the system resources through OS. So capability, in this particular case, if there are too many subjects which are which are allowed access on an object, then the search will become an issue. So whenever an object is being accessed, and if you try to validate the authorization, then the searching would be an issue, and most of the operating system will try to cut on that cost. Now, a capability would be like that this is an object, and these are the access rights for that object. Okay, and it is a kind of a ticket that will pass on to the subject. And if the subject holds a ticket, then he gets these rights, whatever is specified in that capability. So one good part about this is that the rights can be delegated very easily to other objects. So once the capability has been granted, then no further validation of access is required. Whether I included it or not. Okay, now I come to a problem called, before I come to this problem. So, operating system has to keep information about the rights which have been granted to a subject on an object. So it will keep some information like this, that this is a user, and at time 10, these are the times. Okay, this is the time. So at time 10, read write was granted by A to B, and at time 15, the A granted right to B on this table. So on table X, A granted right to B, and the rights that were transferred were read and insert and copy. This means B can, but for B, the rights were given with read and insert only, it was not allowed to copy. And at time 20, B granted, because it received the rights from A and it granted to C. Similarly, C granted it to D. Now B and C can be granting this right only, I think it was with the copy option. I don't recall it right now, okay. Anyhow, so in this particular case, they were allowed to delegate their rights. In some cases, it is not possible to transfer the rights. It all depends upon whether the grantor wants you to transfer the rights to other processes or not. So for example, a parent process is created and a parent process creates a child process. So all the rights which are given to the parent process, should they be delegated to child or not, or should there be some restriction when this happens? So it depends upon the implementation. So in any case, in this particular case, A grants its right to B grants its right to C, and C grants its right to D. And these are the rights read and insert. But then A has granted only read right to D. This is only read right at this point. But otherwise, so D has received read and insert right from C and only read write at A. So from time 15 to 30, D could not do any insertion, but after time T equal to 30, D can do some insertion. Now let's say at time T equal to 40, B, A revokes right of B. So now at time T equal to 40, B does not have any time, any rights associated with it. Now what happens to C? So naturally, so before that, this was the situation. So A has granted right to 10 at time 10, and this was the situation. But now if the rights of B are revoked at 30, then this particular row has to go. This particular row has to go because the rights have been revoked. But after time 10, time T equal to 10, B had granted its right. There's a table and T in which B has granted its right to C. So naturally the C should also go. This table should also go. And now C has given it to D, so this should also go. So ultimately the only thing that remains is that A has transferred right to user D at time 15, and now the insert right for D has also been revoked. So now let's look at this scenario. Okay. So in this particular scenario, A has granted right to B at time T equal to 10. A has granted right to B at time T equal to 5. B has granted its right to B, and so on. So let's look at this scenario. Can you construct the table for this first of all? The way we created the table this way. First of all, create this table, all of you. So how many rows are there in the table? Hello? How many rows will be in the table? Anyone? The operating system has to keep information about what are the rights, and if the rights are being delegated to other processes as the time progresses, so it has to keep some information on who has got what right at what object at a given time. It has to know that, so it has to keep that snapshot. So it has to keep on updating these tables of rights at as and when the tables as and when the delegation occurs, or grant of rights occur, or revocation of rights occur. So what will be the table look like? How many entries will be there in the table? Has anyone answered on the chat? Five entries. So let's look at it. Five entries. So let's look at it. So there are five entries shown like this. Your order may be, I kept it as per the time in which the rights are granted, okay? So the rights are granted by A at time T equal to 5, to D, then to 10, 15, 20, 25. Now what happens if the right of B are revoked? So if right of B are revoked, then what will happen? what happens if A revokes B's right at t equal to 30? So when it revokes right to B, so naturally this table has to go. And now B has granted right to C, so these two also have to go. But still there are rights of B because it got them virtue of B. Okay, so what happens? So if we delete this these tables, then what will happen? A granted the right to B, this is revoked. So any right which was passed on from B to C will also be revoked. The situation will look like that A has given right to D and B has given right to B. But B had already given some right to C also. So because B was retaining that right, because by virtue of D, then this right will also be retained by C. So that will be the change. So this table will not be deleted, but this will be modified, and that would be the change. So now let's come to a problem that is known as confused DPT problem. This problem was actually found in one of the companies which was actually providing access to Photon compiler through their services. So Photon compiler was installed in some directory, let's say call it system, sysx. And naturally, whenever someone was using this compiler, so naturally the company will charge the bill to the persons making use of the compiler. And then whenever the file was being compiled, whatever was the statistics generated at that time, whether the compiler was able to compile the file or whether there was some error or something else. So this was being written in this folder, this file. So one of the file was written to the directory as bill file and another was written as stat file. Now this file was privileged, only the compiler could write into it. And so usage of the Photon compiler was something like this, that I want to call the Photon compiler within sysx directory. This is the name of the input file and this is the name of the output file. So the user will give this command and the Photon compiler will run, take this input file, compile it and generate output file. At the same time, it will also generate the bill. Now, what if a smart user says that the name of my output file should be sysx bill? What will happen? The Photon will run, take the input file, Photon will run and write to this particular output file. But this file was where the bill was to be written or bill had been written or earlier bill was there. So this particular file gets overwritten and this gets complicated. This gets modified or corrupted. So this is what actually happened. And the problem is here now, the user was allowed to give this command. And the service was supposed to launch Photon on this input file and create the output file as given by the user. But as far as user is concerned, user did not have any privilege into sysx directory. The only privilege into sysx directory is by the compiler. So while this file is being written, well, the compiler had access to sysx, so naturally it could write to this file. So there was nothing wrong as far as the authorization was concerned. The only thing was that system should have verified whether the user could have given this name or not. Okay. So now if you look at the compiler is acting like a deputy. And this compiler is being invoked by the user. So the compiler is serving this master and running compiling the process. And the other authority of the compiler is because of the system itself, the license that it is having. So when it is running when the compiler is being invoked by the user, it should not be allowed to access the privileged directory. But when it is running because of the license, then it should be allowed to access the privileged directory. Okay, and that is what was creating this problem. So uh, the problem is that compiler doesn't know which is the privileged area or which is not privileged area, because compiler code will simply look at the file. Compiler code was supposed to read the input of the file. Let's look at the initial part of the compiler. It is looking at the input of the file and the output name of the file. So it reads the input file, compiles it, and writes the output to the output file. And then the code will run for generating the bills and all that. So if it is overwriting, okay. So the problem is that sysx is a privileged directory, is the view of the implementer, not the view of the compiler. So somehow smart invoker has tricked compiler in granting rights of license file to the invoker. So basically there are two masters. So one master has tricked the deputy in serving him as he would have served for the second master. So the first master has acquired the privileges of the second master. And this is known as confused deputy problem. And so one problem is that you have to actually look at the role of the compiler. So one is that as per the role of the compiler, the privilege accesses should be checked. But a simpler solution is that now, as far as the access control list is concerned, as I told you that as far as the access control list implementation is concerned, no violation is taking place. So compiler is allowed to access the sysx area. Yes, it is allowed to access the sysx area. The problem is at some time it is allowed and at some time it is not allowed. So how would you implement that in access control list? So a solution that emerged from this was that we should implement it as a capability. So initially the capability of the compiler is that it cannot access the privileged area. And then later on the capability would change and it can be allowed to access. So depending upon the hat, its capability could be changed. So an easier solution to mitigate this confused deputy problem was make use of capabilities. In fact, the capabilities came into the picture because of the confused deputy problem itself. Okay. So in this particular case, because user is also, so the capabilities would be implemented like this. User is allowed to invoke the compiler, yes. User is allowed to read and write input file, yes. User is allowed to read and write output file, yes. What about anything in the sys? User has no access. So naturally, even if the user gives the name as output file as a sys bill, because it doesn't have any access on that, so this particular operation would not take place. And the good thing about this implementation is that this capability list, once the sys is shown as a privileged directory which is not allowed access to user, anything within the sys will not be having any time of the user. So even if in another scenario, the name of the privileged directory changes from sys to, let's say, system or something else, the same situation will appear. So capabilities will allow us to ensure that, so now here there is a distinction between user and compiler which is running on behalf of the user. So there is a distinction between that. So as a result, the user may invoke the compiler, but when it invokes the compiler, because it does not have any rights in sysbill, the very first time it gives its command that the name of the output file is this, that command would be rejected. So other examples of confused DPT problem are CSRF, cross-site request forgery, cross-site scripting, click checking, FTP bounce. These all are examples of confused DPT. For example, let's look at an example of click checking. What happens in click checking? In click checking, the user is clicking on a certain widget on the screen. So basically, the web page is shown as multiple GUI objects, and some of the GUI objects can be clicked by the user. Now, what the adversary has done, what the attacker has done, he has created some widgets which are not visible to the user, but they are actually imposed on the widget of the application. So, for example, there might be a message box. On message box, there are two buttons, OK and cancel. So on let's say OK, another widget is appearing which has the same color as OK, and so it is transparent and it's not visible to the user. So when the user clicks, but this widget is on top of OK. So as far as system is concerned, when the user is clicking that transparent button. So whatever click is being generated by the user is actually accepted by the transparent button and not the OK button. But what user is seeing is an OK button. So here, when the user is giving permission for certain operation, so this click has been hijacked by. So as far as the system is concerned, the browser is concerned, browser doesn't know the real intention of the user, and he will actually the browser will run accordingly and execute the task which was done by the invisible button or transparent button, the button which was not visible to the user because it has the same background as the actual button. Similarly, is the cross-site request forgery, in which the server is not able to distinguish whether the request has come from the real user or a malicious user. So basically, malicious user has stolen the cookie from the user, and using that cookie, he has established that he is also the real user. So the server cannot check that. So similarly, you can go through cross-site scripting and FTP bounce. These are other examples of confused equity. Now, generally, most of the time, the problem with the access rights is that they do not deal with time. So access rights should also be changed with time. And then we are going to talk about access rights are just checking whether the user has access or not. But what about information that is flowing through the system? For example, one user can read some data from the file and then copy, and let's say this is a privileged file. So one application on one user reads data from a privileged file and then writes it into a public area. Now from here, the other users can read it. So basically there is a information flow in which the access violation has taken place. So a privileged user has abused his privileges and leaked the information. Now this again could be accidental or this could be intentional. So we need to check for this information flow also and see whether this information flow is with or without permission. So for example, many of the apps, let's say app A read some data about, let's look at two apps in a smartphone system. Now in smartphone system, some apps are allowed access to your sensors, microphones, camera, file system, not file system, Microsoft camera, gyroscope, Bluetooth, etc. And other app, and generally, if we do not allow any internet access or SMS access, so most probably the data that this file is that this app is reading, this app is not able to copy that data to any outside source. So there might not be any leakage, and we might feel safe even while the app is reading data from the sensor. So one thing is that if we block the access of this app to any outside medium through Bluetooth, through NFC, through internet, so quite possibly that this app might read the data, but then it cannot transmit it outside the smartphone. And let's say there is another app which has access to outside the world through SMS or through voice calls or through internet, etc. Bluetooth, near field communication. So this app is basically able to interact with the outside device. So let's say there is app 1 and there is app 2. So app1 can read data from the sensory devices, but it is not allowed access to pass on this data to the outside world through communication channels. Whereas app2 is acting with a communication channel, but this is not able to access any of the hardware information. It cannot read any device information. So is the system safe? Now this is as you know that in case of smartphones, user is the one who's granting the permissions. So naturally app2 cannot read any data because no permission is there. But what if app1 reads the data and writes it to a, let's say, log file, which can be accessed by any other process, or it creates a small database to which it allows access to app2. So now this has created an information channel in which app1 has read the private information of the device and put it into the database from where the app2 is reading. So if app1 and app2 are collaborating or colluding, then there is created an information channel in which app2 has gained access to the data to which it has no permissions. So this is, so information flow. The problem is that most of the modern, in fact, I don't know now, but up to Android 6, there was no checking of whether this information flow could exist or not. So the problem is, one thing is that you are allowing access to the data, and access to the data should be allowed to the authorized person. And the second thing is that when the data is being passed on from one user to another user, data or part of the data or modification of the data. So we will call it data also. For example, if I'm reading X and passing it as X square, so any operation done on X is still keeping information about X, and passing that information on could also be as leakage of X. So for example, if I divide X into bits and I pass one of the bits to the other process, that is also a leakage. So when I talk about X, the data that is being leaked, it may not be X itself. It may be any function applied on X. Or so whether I'm leaking in part, or whether I'm leaking it complete data, or whether I'm leaking it as modified data, all of those things will mean a leakage of the data. So whenever X is modified or broken into parts or encrypted, then I will still assume that this new data, which is keeping information about something of X, is also equally private or equally sensitive. So leaking that data is also problematic. So one thing is that we allow the correct authorization to the data, and second thing is, once the authorization has been allowed, then we need to check how the data is flowing from one user to another user. So information flow is equally important. So generally we will be talking about security classes, and so generally this is top security class, this is highly confidential, this is confidential, this is something like this. So information can be allowed to flow from within the class. So as long as this is, so if there are 5 people working on a project, and that project is of very high importance from the national security perspective, then actually they can pass information to each other because they are part of the project. So if there is any leakage, then the leakage could have come from these 5 only. Okay, so naturally, because they all know about the project, so they all become equally, they have to be equally responsible for ensuring that there is no leakage. So within a class, the information will be allowed. Now, is it allowed to flow from a lower security level to higher security level? Yes, it should be allowed. But can it go from higher security level to low security level? No. Or some unknown class about which we do not know? No, it should not be allowed that. So, so this is an example. So when we say that we are copying file 1 to file 2, sorry. So this is what I was trying to say, that even if we modify the data and pass part of it, it is still an information flow. And in this particular case, X is assigned to Z and Z is assigned to Y. So this is an indirect information flow. So through the actual data was Z and there is no information from so the actual data was X. Actual data, the sensitive data was X. So there is no direct channel between X and Y, but there is an indirect channel via Z. So this should also be permitted. And this is actually a very difficult thing to ensure that this doesn't happen that way. We'll come to it later on. So this is also some kind of information about X is being passed to Z. So all these are examples of information flow. So if we are saying that F is set of all possible flows in an information flow system, and P is the set of the flows which are authorized by a given flow policy, and E is the set of flows which are permitted by the implementation of our flow control mechanism, then what we would like that P should be a subset of F and E should also be a subset of F. This is what is taken for granted, isn't it? E cannot be a superset of F and P cannot be superset of F. As long as the set of the flows that can actually exist in the current implementation is a subset of P, well, we are happy because it means every executable flow is authorized and system is secure. And system is precise if E is exactly equal to P. But would we like E to be a superset of P? No. It means if this happens, this is not permitted. If this is happened, it means there are certain flows which are not actually authorized by the system. So there are some flows which are leading to information leakage. So information flow channels can be actually divided into three parts: legitimate channels, storage channels, and covert channels. Legitimate channels are the channels through which the information flow is permitted. Covert channels are difficult. Let's look at what we mean by the covert channels. For example, let's say a user is doing something on the screen. Is that right? And let's say there is a mirror behind the user. And let's say a part of the information is visible in the mirror. So now this mirror is acting like a covert channel. Or let's say even if the mirror is no mirror, let's say no mirror, I'm doing something on my system and attacker is sitting in front of me. So naturally, when I'm doing some processing, depending upon the processing, what I'm doing, let's say I'm displaying something on my system. So some of the colors on my screen will change, and this will change the intensity around my screen. So by looking at the changes in this intensity, the attacker may try to guess what could be the he may try to infer something. Third thing, it would be the covert channel would be the power consumption. So if your system is doing a very compute intensive job, it will require more power. It will start getting heating up. So this temperature and power can be an indication of whether I'm going for like some compute intensive job, which could be related to encryption, decryption, or which could be related to some kind of copying data on the file or something, taking backup or something related to that. So it could give some information, indirect information to the user. Another thing could be like in case of your mobile devices, the data may not be directly leaked by known communication channels, which are your Bluetooth or near field communication or internet or SMS. It may be leaked through, let's say, because your mobile phone is able to receive certain frequencies and is able to transmit frequencies because you are speaking something. So it is a transmitter also. So what if the transmission range is beyond the inaudible spectrum and something is leaked through that? So yes, that is a covert channel. So there can be multiple covert channels. So covert channels are the channels which are not actually intended for the information transfer, but they can be used by the adversary to know about what the information flow is all about. So actually, the legitimate channels, they are simplest to secure. But covert channels, well, it depends upon the ingenuity of the attacker to see what can be used as a covert channel. So you cannot always foresee what can act as a covert channel. So there are two information flow models. One is focusing on the data confidentiality. This is Bell-LaPadula model. And then we'll talk about another model, which is basically about the data integrity, DIVA model. And the problem is that both models are conflicting each other. So if the data is confidential, there are two rules two are mandatory access control rule, and one is the discretionary access control rule in case of Bell LaPadula. So simple security property is that a subject at any given security level may not read an object at a higher security level. So there is a top confidential security document. So the normal user is not allowed to do it. For example, let's look at a classroom scenario. So there is a question paper. So only teacher has, before the examination, only the teacher has access to that question paper. The student should not have access to that question paper. So there are two security levels. One is for teacher and one is for the student. The student cannot access the document. Now, second thing is a subject at a given security level may not write to any object at a lower security level. So it means a person who has got a higher clearance should not accidentally write something on a document which has to be passed on to a person with not having that security clearance, which can have an indirect leakage of the information. So this is no write down. So they should not be allowed. No read up means I cannot read any document which is having a higher security clearance than what I have got. And I should not be allowed to write to any document which has got lower security clearance than I have. So these are the two mandatory access control rules. And then discretionary security accesses. At times I may have to pass on the information. For example, when I'm distributing the question paper, or maybe I'm making some correction to the question paper, then I may have to pass some information to other entity. So this is the discretionary access control. So the point is that we need to remember is the read down is allowed, write up is allowed. But the main problem with this would be the data integrity. We'll see how. This is one of the examples. So as I said, this is not concerning the data integrity. So information can flow from low to up, but then the problem is when it is flowing from low to up, then quite possibly it can also so what we said was in this model, we said that I cannot read a document which is at a higher level. I cannot write to a document that is at a lower level, but I can write to a document which is at a higher level. So I can write something and pass it on to my officials, and this can corrupt the data. Okay, so this is where the problem is. So for example, there are three security levels. Clerk has the least security level, then programmer has the mid security level, and company CEO has the highest security level. So a programmer can query a clerk about the company's future plans and override the CEO's files that contain corporate strategy. So basically, this has corrupted. So information has flown from low to high. That is allowed, but it can have integrity issues. So BIPA model is actually concentrating on integrity. So it prevents data modification by unauthorized parties, prevents unauthorized data modification by authorized parties, and maintain internal and external consistency. So subject may not corrupt data at a higher level. Data corruption from a lower level than the subject not allowed. So maybe you can read more about it. And I will also ask you to read more about this also. CSRF, CSS, and FTP bounds. So these will be the assignments for today. And now let me pose a question for attendance. Quickly. So next week is our last week, correct? I think the classes were for up to, okay. So on Monday, so let's keep it for revision. Okay, so I can have a short video, so we can discuss our answers. We can discuss all answers to the questions that I have asked. Okay. In lab, I was supposed to uh, to assign only 50% assignments. So you are required to do rest in person when you visit campus. So that's why I have not loaded you more on lab work, but I think I will give you one more assignment in the lab. And what we can do is we can, when are you coming to campus? When are you reporting to campus for examination? On 15th of March. Okay, so thank you so much. So I think then your midterm and end term examination as well as the remaining lab work will also continue. So what I will do, I will continue with this. I'll give you one more lab assignment, and I will share all the slides with you till now, today, and then we can start discussing whatever assignments we have been, whatever question I've asked you as an attendance or more, wherever you have doubts, so we can actually start discussing that. So let's keep it as a revision week this time, and see you all on 15th. So have a nice weekend. I hope I can keep it nice. I do not give you very tough assignments, so I hope this will be nice. So see you again next week. All of you meanwhile answer the question on the attendance. Thank you so much for being here. I might also in the next week keep some quiz, okay, just to assess your knowledge. So see you all. I'm closing the session.